We're going to talk about how to select the correct analyzer for the job. We'll talk about best practices for sample preparation and measurement, otherwise known as Common Sense 101. You'll see this and you'll say, oh, I knew that, but it doesn't hurt to have a reminder, so you can get the most from your Sindie or chlorine analyzer. We'll go over some low-range calibration tips, and we'll finish out this series with the sample-specific best practices. And as I had stated earlier, there'll be pauses in between each section so we can have questions, so feel free to drop those in the chat or raise your hand at that time. Let's start with using the correct tool for the job. We have a lot of Sindie options. Sometimes this can be confusing, right? So you need to select a sulfur solution that meets your needs. And I'm going to break this down for you and make it very easy. You want to think about Sindies in two dimensions on this slide. You want to think about them in terms of performance. We have good, better, and best. And then also in terms of method compliance, 7039 and 2622. So when selecting the correct tool for the job, here's how I would do it. First, you need to think about compliance. Do you need to just comply with 7039, or do you also need to comply with 2622? Do note that all Sindie analyzers are D7039 compliant. And if you do need the 2622 compliance, another thing you might want to think about is measurement time. Because if you've read the method, you'll know that duplicates are required for samples 100 ppm and less. So this means when you factor in the background time and the duplicate measurement on our generation 2 2622, that can be 20 minutes to run a sample. Whereas if you consider the generation 3, due to the better quality of optics, we were able to reduce the background measurement time. So when you're running those 100 ppm and lower duplicates, instead of it taking 20 minutes, it only takes 12 and a half minutes. Okay, so that might be a consideration for you if you're running a lot of samples. The next thing you want to think about is performance. How low do you need to go? If you need to quantify less than 1.2 ppm, we really recommend the Sindie Generation 3. Okay. Another note on measurement. The Sindie OTG is available. It is our lower cost option, but do note that it requires a 15-minute measurement time for samples less than 500 ppm if you want to consistently comply with the D7039 method. Next, you want to think about some other things like, do you need a chlorine backup? We do have a Sindie plus chlorine analyzer, which will quantify 1.2 ppm sulfur and 1 ppm chlorine. And then lastly, you can think about some optional accessories like an autosampler. We do have 2 models of Sindies that do come with autosamplers. Moving on to chlorine. You also want to select a chlorine solution that meets your needs. The analyzers here can be parceled into good, better, and best as well. And here's what you want to think about when you're selecting the correct chlorine tool for the job. First of all, compliance really isn't an issue because all of our Clora analyzers will comply with D7536, which is chlorine in aromatics, and D4929, specifically procedure C, for organic chlorides in crude oil. The most important thing here is you need to consider the performance. How low and how high do you need to go? Okay, this is before you consider autosamplers, AccuFlow, having a sulfur backup. It's very important that you pick an analyzer that will measure as low as you need it to. Okay. So in our good category would be the Sindie plus chlorine analyzer, which quantifies 0.9 ppm up to 3000 ppm chlorine. And then our Clora analyzer in the better category, which is about 0.4 ppm up to 4 weight percent chlorine. And then our Clora 2XP, which is our best offering, quantifies 0.27 ppm up to 2 weight percent chlorine. Now, some of you might be scratching your head here saying, this is a little bit, these numbers are a little higher than what I've seen on the brochures. And you'll want to keep in mind that the limits of detection on the brochures are the limits at which we can see the concentration, the element that you're looking for. But when you're talking about quantification, that'll be 3 times that limit. So that's why these concentrations are a little bit higher than what's on the brochure. After performance, you'll want to think about sulfur correction, especially if you're measuring anything like crude oil, which has high sulfur, and so you need to think about how you're going to correct. The Sindie plus chlorine analyzer and the Clora 2XP have automatic sulfur correction. That is that the sulfur is measured at the same time the chlorine is being measured, and then the correction is done automatically. For the Clora, you actually need to know the concentration of the sulfur beforehand and input that before you measure the sample. Next, you want to consider some accessories and things like that. Like, do you need a sulfur backup? Because our Sindie plus chlorine analyzer will measure and report the sulfur concentration. Okay. The Clora 2XP, although it has the automatic sulfur correction, it does not report the sulfur content. That's the sulfur is measured for correction purposes only. And then lastly, you would consider things like autosamplers and AccuFlows. And just a quick word on autosamplers. We really do not recommend these for crude oil measurements because, as most of you know, chlorine is not stable in crude oil, especially when you're talking here about the salts, the salts in the crude oil. So we don't recommend an autosampler. Instead, you'll want to consider something like AccuFlow, which I will talk about a little bit later in the presentation. Moving on, let's talk about best practices for sample prep. Common sense. Keep things clean if you want to get good measurements, right? You need to keep your prep area clean. Don't leave stuff out. Don't forget to cover your film after making a sample up because you don't want contamination. Use isopropyl alcohol for cleaning purposes. You can clean the sample weight or plunger there in the picture, the primary window, and the sample basket. Okay. And I'm actually going to demonstrate for you here how to clean the primary window and change the secondary window after running through some instructions for that. So the primary window is a stainless steel disc with a thin capped on or polyamide film. And we actually recommend you to clean this daily if you're regularly running samples that are less than 1 ppm. If you're not, I would still recommend that you at least check it daily to make sure that there's no contamination on the window. Now, the first thing to note when cleaning the primary window, very, very first step is to have a spare window handy, okay? You want to have this spare window handy because accidents happen, and you wouldn't want to be down because as you were cleaning the window with a swab here, you accidentally punctured a hole in it. Okay, so make sure you have a spare. And speaking of swabs, we recommend a foam tipped swab here, and we're going to use the reagent grade isopropyl on that. The foam tip swab is better than Q-tips because it's much more gentle and less likely to puncture. And when you squirt it with alcohol, which I'm going to do here because you won't see me doing this later on camera, the thing you do is you squirt the swab and then you want to make sure to shake it off. That excess alcohol may leave a residue on the primary window, so you want to make sure to shake the swab off. And when you clean, it's really important how you hold the swab. If you clean it like this, you will be more likely to break the window. So you want to hold the swab parallel to the window and avoid using excess force. If, even this is kind of making you nervous and you think, well, maybe there's something else, you can use a wetted Kim wipe or a makeup sponge, and then you'd be even less likely to break the window. We do have some customers that do that. And then lastly, after you're done cleaning, you dry the window with canned air. When you're using the canned air, if you get some propellant that's visible, when you're drying the window, you need to repeat the cleaning procedure. Next, moving on to the secondary window. For best results, again, change it daily, or at least look at it daily, to ensure that it's not contaminated or have wrinkles, okay? First step to changing this is you remove the sample basket from the analyzer, and depending on your analyzer configuration, the secondary window will either be located on the bottom of the sample basket or on top of the primary window. When you're getting a new piece of film, we also recommend canned air here to blow off any contamination that may be on the film. You place the film on either the bottom of the sample basket or on top of the window. And then when you're snapping that capture ring onto the window, you want to press firmly using 4 fingers, okay? Because that makes it less likely that you'll have a wrinkled window. So let me stop presenting here so I can demonstrate some of this for you. Okay. And in case you missed it earlier, when I get the swab, I soak it in alcohol and then I shake it off. Okay, just give that a couple quick shakes because you won't be able to see that on camera later. I do have an analyzer set up here. If I can switch cameras. And you should now be able to see the sample basket of the Sindie plus chlorine. First thing I'm going to do here is remove the sample basket. You'll note here in this configuration that the Sindie plus chlorine has the secondary window on top of the primary window. So I'll set that aside. And this also, for these configurations, it comes with a removal tool, which I use to remove that and move the ring aside, take the film off, and now I'm going to clean my window. As I showed you earlier, I have the swab, which I have soaked with isopropyl alcohol, and then I very gently just swipe just like that. And then I take the canned air and dry the window off, okay? And then you go and move on to replacing the secondary window. For this configuration, I wouldn't normally blow off the window right over top of the primary window here, but I have limited camera view, so unfortunately I have to do that. You wouldn't normally do that, of course. So you lay it flat there, you place the capture ring there, and then you're going to, and you'll notice here that I didn't press down evenly, and you'll see I have quite a lot of wrinkles right here, okay? So that happens. So you just take off the window and try again. Inevitably, it always happens when I'm demonstrating this on camera. Oh, did you see that propellant that I got on the window? You don't want to probably use that. So we're going to discard that piece of film. Blow it off. The window there. Drop the capture ring. And there we go. We have a clean primary window and a new secondary window. And then you kind of just get rid of all your garbage, replace the sample basket. And I'm going to come back and we'll look at the presentation again. This chart here is for your reference. You'll have copies of this later. But just make sure you use the correct film for your analyzer on both your secondary window and on your sample cup. Note that the film that you use for calibration is the film that you need to use for sample preparation. Okay. Again, some more common sense advice. If something's disposable, don't reuse it, okay? Use a new cup and film each time for sample repeats. If you repeat analysis over and over and over on a sample cup, you'll get erratic results due to film effects, sample evaporation, and other things. Don't reuse disposable pipettes. You know, if the measurement is worth doing, it's worth doing correctly. Don't wait. Analyze the samples as soon as possible. And when you're removing the sample from the analyzer, just take a second to pull it out and kind of tip the cup here and check the film to see if it's leaking. This can save you some time in the long run if you get in the habit of doing this. And then the last thing you want to consider for the contamination is just take a Kim wipe or a paper towel and wipe off the sample weight or the plunger on the underside of the lid. Most of you know how to prepare samples correctly, but I'll just go over some tips to help you become, better at preparing the samples. We recommend canned air to blow out the sample cups this becomes very important when you're really pushing the analyzer limits. As your concentration goes down, the more effect that contaminants will have. So this becomes very important. Make sure to homogenize your sample bottle. You know this. And actually, you don't need to fill the sample cup all the way up. Okay, 5 milliliters for the most part is good enough. You know, more sample is not wrong, but may lead to plunger contamination. Okay, make sure you use your canned air to blow off the sample film. And when installing the collar, you want to press with 4 fingers. Equal pressure will make the sample cup less likely to wrinkle. Okay, you all know here that you don't want wrinkles are bad when it comes to sample cups. So if you get a wrinkle, you'll need to remake the cup. And when you go to vent the sample, here's one that not everybody knows, is those Chemplex cups have that nice little divot or well in the center of the cup. And you think that's exactly where I want to vent it. But actually, we recommend to not vent there. The reason for this is simple, is that well, when it touches the sample will wick up that well. And if you vent there, you will have more sample come up and settle on the top of the cup. So you're actually going to vent off center with your push pin. And we actually recommend 2 vent holes, a minimum of 2 vent holes for all sample types. Get in the habit of that, so that when it becomes an issue, it won't be. For example, if you're running some isooctane type samples, you can get vapor lock, and what will happen is the film, instead of it staying flat, will actually suck up and be concave. But if you use 2 vent holes, that won't happen, okay? And then of course you analyze the sample soon after preparation. Make sure you use the correct measurement time. If your sample is stable, and actually a longer measurement time, you know, will get you more precise results, okay? Typically in low range, this is a 300-second measurement time, and typically it's 100 seconds in high range. Of course, if you're running a 2622 analyzer, this will have some added time due to background measurement. But I also want to call your attention here to the Sindie plus chlorine high range. You'll note that I have that listed as 300 seconds in red. Normally, when you're measuring high sulfur, you don't need 300 seconds. That 300 seconds isn't for the benefit of the high range sulfur measurement. It's because while you're probably measuring high range sulfur, you're probably measuring low range chlorine. And so you need that 300 seconds to get a good chlorine measurement, provided that you know you have a stable chlorine sample. So that's why we actually have the default measurement time set at 300 seconds on the Sindie plus chlorine analyzer. Let's move on to low range calibration. First, we'll start off with our calibration do's and don'ts. Do calibrate the analyzer when it's needed. That's when your control chart is out of range. Some people like to calibrate, you know, also when you have major analyzer changes, such as an X-beam replacement. Some people like to calibrate on a schedule, a fixed schedule, like once a year, but that's not necessary. It's not harmful, but it's not necessary. Really, the trigger for recalibration should be your control chart, okay? Some other things to consider is consider using matrix matching or correction factors to improve accuracy. Some of our customers like to set up gasoline-specific calibrations. You know, you can do that. I'll talk a little bit more here later on in the presentation about correction factors. Obviously, you'll want to start off with a clean analyzer, okay? We went through the importance of it being clean, so before you calibrate, make sure you have a clean primary window and you change the secondary window. One of the things that might be a little bit new for some folks, especially if you've been in the industry for a long time working with X-ray analyzers, it's typical that you would bracket your calibration, you know, tightly bracket it. So if you're only, you know, going to run a 10 ppm sample, you wouldn't calibrate very high, you would tightly bracket it. But this actually is not what you should do. So you do not want to do this when you're working with a Sindie or a Clora analyzer. We actually still recommend the 0 to 500 ppm calibration when you're running those 10 and 15 ppm samples. And the reason for this is that we use, these analyzers use a weighted calibration. It's extremely linear. I'll talk a little bit more about that. And there is a purpose for these higher calibration points. They actually serve to anchor the calibration slope, and you'll actually reduce some of the error in the intercept. So there's actually a purpose and a reason that you're calibrating this high. And of course, lastly on here, make sure you use auto calibration for best results so that you can take advantage of that weighted calibration, which your standard Excel file, your standard Excel doesn't do. But we have a workaround for that as well. It's very, very, very important to have a good calibration blank, okay? A bad blank will cause a high calibration offset, and you'll get very poor precision at the lower end. So it's very important that you have a good blank. You want to consider substitution rather than using a bad blank. So for example, if you are using a matrix match calibration, the diesel calibration, we would actually recommend that you take that diesel blank and toss it, because most diesel blanks, they aren't blank. They're always contaminated. We'd recommend you to substitute mineral oil for that. And then if you're using a gasoline calibration, I'm not talking about the synthetic gasoline. I'm talking about like a non-synthetic gasoline calibration. Those will oftentimes come with a blank as well. And what often happens is those are not blank either. Those are contaminated. So you want to toss that out and use a synthetic gasoline calibration blank, something like isooctane or an isooctane toluene blend. Also for your note here, I have some counts values, because we sometimes get asked, well, what is a good blank? So if you look here, you can find your analyzer type and see what the typical blank counts should be for your analyzer. And note, you'll get a copy of this presentation later on, so you don't have to feel free to scribble down all the results from this table. And of course, lastly, read the user manual. There's a lot of good information in there. Now I'm going to proceed to talking a little bit more about AutoCal. Most of you already know how to do auto calibration, so I'm not going to go through that. If you need some more information for that, why don't you drop your name in the chat, and if there's some time at the end, we can actually review the auto calibration, but in theory it works like this. You run a series of 6 samples. And then you go into auto calibration, which is this menu here in the picture, and you tell the analyzer what those calibration points are. The first sample that you ran will be in position 6, and the last sample that you ran will be in position 1. And you'll see on the right there is the CPS, counts per second value. So that's your total counts divided by your measurement time. And you simply just enter the concentrations, and the analyzer does all of the calibration for you. Very simple. But what happens when you get a bad calibration point? Because you only have 6 spots for AutoCal. A lot of people aren't aware of the replace feature. What this does is the replace feature allows you to replace a point in the calibration. So when you replace the point, in the next sample that you run, instead of it going into position 1, it will replace the number of the calibration points. So say, for example, calibration point 3. I didn't like that one. So I would go over to the right and touch that red asterisk, type in 3, and then touch replace. When you exit out of AutoCal, you then run that standard, and that point will then go into spot 3 in this auto calibration queue. Okay, so this is a very handy feature, because previously people would think you would just have to rerun all of your calibration standards. And I'm here to tell you, you don't have to do that, okay? Use the replace feature as often and replace as many of the points as you want, so long as you do it one at a time. And note that this replace feature can only be used during the AutoCal process. But what if you want to use more than 6 points? That's another common question we get. So one of our tech support persons, he developed this worksheet. It's called the CalRevF Excel worksheet. And this actually mimics the exact same calibration process that the AutoCal uses. So you simply just type in the values like you would in AutoCal, and you get the return information there on the right. So what you do is you enter the accepted reference values for your calibration in that first column, a yellow column. And then you enter the total counts time in the second yellow column, along with the measurement time. And then on the right, you'll see up towards the top, you'll see the calibration slope and offset, as well as the correlation coefficient and the residuals, okay? Like I said, the key feature of this sheet is that it does the weighted linear calibration, but it allows you to use 6 points, okay? The other thing I like about this sheet is you can see the R value and the residuals, you know, before they get entered into the analyzer. So you can be aware that there's a bad point. So here in this worksheet, you'll see it flagged there in red. And then once you get the calibration you like, so you would then rerun that point, that bad 500 ppm point, put the new counts values in, and once you're happy with that, you would enter that calibration, the calibration factors into the analyzer using manual calibration. But I often get asked, how do I know I have a good calibration? So remember this red outlier here. I'm going to refer to this in the next slide. What you want to do to determine if you have a good calibration is you want to look at the R value and look at the residuals to determine if the calibration is good or bad. Okay, that you can find it by pressing the stats button on the calibration curve screen. Note that's not available on the Sindie plus Chlorine, so you can get that value from the CalRevX worksheet. Okay, R is your correlation coefficient. It should be very close to 1. So I talked earlier about how we have a very linear, we're extremely linear. How linear? The guideline is that if you get 2 9s for your correlation coefficient, that's actually a bad calibration. You should get at least 3 9s, and you should aim for 4 9s or better to get the best calibration fit. Do note that the narrower the calibration range, the harder it is to get a good fit. So oftentimes for the Clora 2XP that uses a 0 to 10 ppm calibration, 3 9s is often the best that can be gotten on that because of that calibration range is smooshed. Okay, and then how do you improve your correlation coefficient? If what you can do is you would consider replacing or removing points to improve a fit. Sometimes you just get a bad calibration standard. It happens. So you can actually remove that and you will improve the fit of your calibration. Oftentimes, though, what people want to do is they'll want to replace it using that replace feature. But which ones do you replace? You look at your residuals for this, okay? And the residual is the difference between the measured point and the calibration curve. The residuals must be between -3 and +3, or they get flagged as an outlier in the previous slide in red, okay? But if you're really looking to maximize your calibration and have the best calibration possible, you want those values to be smaller. For better results, they should be between -2 and +2. But for the best results, you want to look for residuals that are between -1 and +1. And in order to do that, you would consider rerunning and replacing those calibration points as needed to improve your calibration. So we put in our calibration and we're very satisfied with how it looks. So we're all done, right? Let's go celebrate. Wait a minute, one thing. Don't forget to run a calibration check. Okay, your calibration's not done until you've confirmed that your calibration is good. So what is a good check? I've compiled a list here of some references that are useful. You can look to your existing control chart if you have one. You'll have upper and lower control limits, so this will give you a plus or minus for your check sample. You can purchase a NIST SRM. You know, that comes with check sample limits. A caution here, though, that's not the same as a calibration standard with the C of A. You'll notice if you look at the C of A, it says calibration standard uncertainty. That is the error in sample preparation. That does not take into effect any error in the measurement. So you don't want to use that as your check sample limits. Another place you can get them for, so we're in Canada now, but if you're exporting gasoline and diesel into the US, you can look to the EPA. They have here a series of equations for accuracy, and they actually even for precision as well. So they have a lot of good information here about appropriate check limits. You can also turn to the methods. For the test methods that specifically call out the monochromatic excitation, which would be D7039, 7536, and 4929, you'll see a statement in there at the end of the calibration section that says that your check samples should be within plus or minus repeatability. Okay? This is especially handy when you have a new analyzer and you don't have a control chart set up yet. And of course, if you look in 2622, there's a similar statement, although it says that the differences between two measured values shall be within the repeatability of the test method. Okay, that's the section on calibration. Do we have any questions here? Pause for a moment.
We don't have any in the chat.
Okay, well, I'll move on and let's talk about some sample-specific best practices. We talked about correction factors earlier and why they might be used. Let's talk about oxygen. If you run an oxygenated sample on a mineral oil calibration, you are going to see a low bias. And this is because oxygen absorbs sample X-rays. So those sample X-rays, they never go to the optic, the second optic here, or to the detector, and you get this low bias, okay? And you can use correction factors to mitigate the effect of oxygen absorbance. So when you're measuring a biodiesel on a mineral oil calibration or an E10 on a mineral oil calibration, or we commonly get asked about water. A lot of people end up running water on their Cloras, and the correction factor for that is 2.5. That means that it measures 2.5 times lower when measured on a mineral oil calibration. So in order to correct for that, you take your measured value. In this case, it would be 10, is my example. You multiply it by the correction factor to get your oxygen corrected value. The last thing to note is that if you have a Sindie 2622 and you're in 2622 mode, note that you can use the correction factors in 7039 even though you're running 2622. This is because the basic analyzer geometry hasn't changed in between modes. You're just merely running a background measurement. So those correction factors that are in 7039 would be applicable for 2622. Here I have a series of tables that I'll show you for reference. There is, here's our biodiesel correction tables. The top one is for chlorine, and the bottom one is for sulfur. So say, for example, I want to measure a biodiesel sample, and I know that that biodiesel sample has about 11% oxygen in it. So you would find that correction factor by looking at the intersection of the values on the first row and in the first column. So 11 is 10 plus 1, and the correction factor would be 1.1914. And you would multiply that by your measured value to obtain the corrected value. Here are a couple more tables. These ones are in ASTM's D7039, and they are the correction factors for oxygenated samples. So if you're measuring E10 on a mineral oil calibration curve, you can look up the factor. It's 1.0556. And then the second table is if you have set up for an ethanol calibration, such as like E85 or E75, if you want to measure that. Next, let's move on to chlorine. A lot of people know this, that chlorine doesn't behave the same as sulfur, especially when you're talking about crude oil. You typically have salts in crude oil, which are not stable. And so if you were to take a raw crude oil and stick it into a sample cup and measure it for 5 minutes, walk away, you'll come back and the number will be high. Because what's going on is those chlorine salts are settling over time. If you look at my example here on the left, here is a Western Canadian crude oil sample that I took 30-second snapshots for a measurement time of 3 minutes. 3 minutes! And look how much this sample settled. The standard deviation, not so good. So one of the things you can do is consider using AccuFlow, okay? This is applicable for samples up to 2,000 centistokes at room temperature. And one note, when you're measuring total chlorine in crude oil, don't forget sulfur correction if the sulfur is above 0.5% sulfur. Let's look at this graphically, okay? Same data as before. In black, you have the static sample, and you see that it's increasing over these 30-second intervals. And the colored samples there are AccuFlow runs. And what AccuFlow is, and unfortunately, I do not have an analyzer available to show you that, but we do have a video we can reference later on, or if you're interested, drop your name in the chat, and when we get an analyzer back in the lab, we can set up an AccuFlow demo if you're interested in seeing it in person. Well, in person. But what you'll see here is the AccuFlow basically mitigates the settling of the chlorine. And the way it does this is you take a syringe that's filled with 60 milliliters of crude oil, and it is continuously injected during the measurement time. So the chlorine doesn't have a chance to settle because it's being pushed through the measurement area and then collected on the outside of the analyzer. Okay, so this is one way to handle it. This is probably the best way to handle the settling if you're just looking at the total chlorine, but perhaps you don't have AccuFlow. So we do have a static screening technique. We actually have, there is an oil major that actually uses this technique as their way of measuring chlorine. And what you do is essentially you're going to take a sample cup, static sample cup, and you're going to use a shorter measurement time with repeats. And what you do is you essentially shake the sample or swirl it in between repeats so the chlorine doesn't have a chance to settle. Do note that, okay, for starters, the chlorine is not stable, and so it's still trying to settle. And also that these are a 30-second measurement. So this is why we call it a screening technique, because we do not expect this to be precise. This is just to give you an idea of what's actually in that sample. One of the things that helps is if you get a laboratory mixer or a sonicating mixer to homogenize the sample, okay? And then if you run the sample, if you've ever looked at the repeat menu on your Clora analyzer, you'll notice that there is an option for measurement time, number of measurements, and then this thing called repeat delay. And what the repeat delay is how many seconds before it starts the next measurement. But what's interesting about this is if you set that repeat delay for 10 seconds or more, actually the first time you try this, you probably want to set it for 15 seconds. And when you set it for 15 seconds there, the lid will actually unlock between the measurement. So what you do is you put your sample in, you swirl it, you put it in, you measure it for 30 seconds. And when that repeat delay is 10 seconds, the lid unlocks. So you open up the lid, you reach in real quick, go like this and put it back and measure it. And you do this repeatedly. And so that way you can look at your printout and you have all the statistics computed rather than running 3 individual measurements and then hand averaging them. Note that this technique is ideal for the medium viscosity type crude samples. If it's a very low viscosity, it's still going to settle during that 30-second measurement time. But what about the other extreme, high viscosity samples? What do you do for chlorine in high viscosity samples? It's not settling because the samples are semi-solid or perhaps solid at room temperature, so it's not settling. But the problem is that the chlorine is non-homogeneously distributed. So when you measure it, it depends on where your focal point is, what chlorine you're seeing. So one of the things you can do here is that you look at different focal points in the sample, and then you take the average of that and this will tell you what's actually in there, rather than measuring one focal point several times. You get a better idea of what's actually in the cup if you look at the different focal points. And I'm doing this with my hands because what you're going to do is when you set your cup up, you're going to do very similar to what you did before. And you're going to set that repeat delay for the 10 seconds, and you're actually going to reach in and rotate the cup. And that is enough to get it to look at a different focal point. And you do this for about 3 measurements, anywhere from 60 to 100 second measurement time, depending on the concentration of the chlorine. And you reach in there, and when you do that, you're looking at these different focal spots, and you get a printout with the statistics already computed for you. One note about these high viscosity crude oil samples is, of course, you're going to have to heat them up to get them in the cup. Now, earlier I mentioned that 5 milliliters is sufficient for most samples. Well, here's the exception, okay? In this instance, you're going to want to fill the cup up 2/3 to 3/4 full, because you want to make sure that there's enough sample when you invert the cup. Because, of course, the crude oil is going to stick to the bottom and the sides of the cup, and you want to make sure enough sample gets down and goes on top of the film. The other thing you want to note is, because you've heated this sample up, okay, what happens as the sample cools is the film, which is flat, will concave. And what that is without that flat film surface, you don't get an accurate measurement. It'll actually bias low because it changes the focal point. So what you do is you vent the sample at least 4 times, as this will keep the film from concaving, okay? And then you go ahead and measure that immediately. Don't forget to use sulfur correction, as these types of samples generally have sulfur in excess of 0.5%. The next thing I want to talk about is, well, one of the things we haven't mentioned is I kept talking about total chlorine. But what if you need to measure inorganic chlorine and organic chlorine? X-ray, by definition, only does total chlorine, okay? Doesn't matter whose chlorine analyzer you have, it's total chlorine. So in order to see if you have inorganic or organic, you do some sort of sample preparation. We have here a very good paper that talks about oil extraction. Most of you are probably already doing this, but if you don't have one set up, you can read this paper, and it will give you, the ratio 3:1, and it'll walk you through the calculations, and so that when you had diluted the crude, with your solvent and then with your water, that you are then correctly back calculating for these dilution factors. So this paper will walk you through that. The other topic of this paper is ASTM D4929C. In 2017, this method was updated to include an X-ray. This includes all types of X-rays, including MWDXRF. And this method will walk you through, you still do the same naphtha distillation that you do, and you just instead measure it by X-ray. But if you want a little bit more detailed information on how you would do this on the Clora, you would go ahead and look at this paper. Lastly, I want to finish up with a topic that we often get asked about. You'll notice throughout this presentation that I have been using the word chlorine. But what you're measuring and what you care about are chlorides. So what's the difference? So chlorine in the petroleum refinery typically refers to one of 2 things. As you know, the chloride anion, which is that chlorine atom with that extra electron in its outer bonding shell, for example, sodium chloride. Okay, this is your inorganic salts. Or it might be an organochloride, where it's bound to carbon, okay, with an RCl kind of configuration. Okay, that's an organic chloride. And note that both of these chlorides, it refers to what's going on in the outer or bonding electrons in the chlorine atom. And the reason that we use the terminology chlorine is because the Clora detects the presence of chlorine atoms by looking at the inner shell electrons, the K alpha to be specific. Okay, the Clora does not know the status of the outer shell or the bonding electrons. So therefore, your Clora actually measures all chlorine, including chlorides. Okay, Clora measures chlorine atoms by weight, no matter the molecular structure, right? Sodium chloride, hydrochloric acid, organochlorides, technically even chloride gas if it were dissolved in a liquid, okay? This is total chlorine. Now, if you think about the type of samples that are present in the refinery that you're looking for chlorine, such as crude oil, water, naphtha, those are all present in the chloride form, okay? So you think about it like this. If the only chlorine compounds that are present in the sample are chlorides, and if the Clora measures total chlorine, then Clora results can be reported as chlorides, okay? Another way to look at it is that chlorides and chlorine are present in the sample in a 1-to-1 ratio. Okay. This concludes today's presentation on the Sindie and Clora best practices. We're going to stop and pause for any questions before Joe walks us through the Petra. Do we have any questions?
Just got
one did.
chat.
Yep,
Okay, I'll read that. In my lab, when we test sulfur on gasoline samples, we shake and homogenize the bottle before running. We get a high sulfur result that is off spec as a QC LCS check. If we don't shake the bottle before running, we get a lower sulfur result that is on spec as a QC check. Is this normal, and does the sulfur settle on the bottom of gas samples? I'll be honest, this is a little strange, because what this is indicating is that there's something in there that is settling out of sample, perhaps, and that when you shake it, it's giving a higher concentration. Typically, you don't see this. The sulfur, you know, it should be homogeneous typically in these things. But the other thing I want to maybe point out to you that might be going on is take a look at how much sample you're putting in the cup. Because if you don't put enough sample in there, you may have air bubbles and the sample is not homogeneous. And so that might cause it, but that does not answer it if you prepare them the same way. So I'll be honest, I'm a little puzzled by this. We can talk a little bit more about this offline. Would you recommend cleaning the pins for puncturing holes in sample cups between running different samples? Absolutely, I would recommend that, especially if you're switching between high concentration and low concentration samples. That's actually one of the reasons that we recommend when you're calibrating that you start with the low concentration sample first, because it's then less likely to contaminate the other samples. So if you forget to clean that push pin, the other thing is some people will just use a new push pin for each sample. Up to you, but yeah, that's a very good idea to clean the push pin. Okay, waiting a few more seconds. Otherwise, Joe, I'd like to turn this over to you.
All right, great. So next I'd like to take everyone through an overview of our the Petra series, which consists of two analyzers, the Petra Max and the Petra 4294. And we can ask questions just similar to the last session if you want to put them in the chat. Oops. And just really quick, XOS has been around several decades, but in 2011, I believe it was, Danaher, a very large holding company, purchased XOS, and all of those companies are owned by Danaher, entirely pretty much in the scientific world. All those companies, some very familiar to many of you, I'm sure. And now XOS is part of that family. All right, so just an overview. So again, we have the Petra Max and the Petra, both compliant with the Sulfur 4294 and also the ISO 8754. With LOD, the Petra Max is 5.7 at 600 seconds, and the Petra 4294, the Sulfur only, is 2.6 ppm LOD. at 600 seconds. And the Petra Max has the added capability of 12 additional elements to sulfur, including nickel, vanadium, and iron, very of interest to the crude oil world, of course, at sub-ppm levels. So, you know, most of our customers are testing materials, hydrocarbons like crude oils and jet fuels, refinery process streams, some diesels and gasolines around the world, including Euro 4, bunker fuels, and some lubricants. The Petra Max, again, has those additional elements, also complies with the 4294. On the left, you'll see it's just a chart with the LODs for each of the elements that the Petra Max is capable of. The dynamic range is ppm levels all the way to weight percent in multiple elements. The Petra Max, like the Petra, has the advanced software features for enhanced workflow and for simplified data collection. Also, we do have available an 8-position autosampler with QR scanning technology, and I'll give you a further update on the status of our autosampler a little later. Here we're just showing some precision data, essentially, some repeats on a sample, testing sulfur, vanadium, iron, and nickel. You'll see with 10 repeats for sulfur, around the 4,700 ppm range, we got a standard deviation of 41. With the vanadium sample with an average result of 0.3, a very tight standard deviation 0.04. And with iron sample averaging 0.5 ppm, we have a standard deviation of, again, 0.04. And then a nickel sample averaging 2.5 ppm, standard deviation of 0.03. So some good tight precision there. The Petra 4294, again, that's the sulfur only analyzer, complying with 4294. That dynamic range is 2.6 ppm up to 10% weight. Also that advanced software for the workflow and simple data collection. And again, just like the Petra Max, the auto sampler 8 position would be available for that. So I just want to give you, we'll compare what we'll call traditional EDXRF versus advanced HDXRF, which is what XOS does. So when we say traditional, it's sort of referring to what our competition has out in the field. So give you an idea of how traditional EDXRF works. So you can see in the diagram that an X-ray source exposes a beam of polychromatic X-rays straight to the sample. Peak incident X-ray energy from the source selected is based on the element of interest. All other X-rays are unnecessary and they create spectrum background, which of course degrades measurement performance. So that's traditional. Continuing with traditional, next is peak energy from the tube ejects electrons in elements of interest in the sample. Electrons then move to fill the gaps, and this process creates a fluorescent X-ray signal that can be used to calculate the elemental concentration in the sample. Note that peaks in the energy spectrum are proportional with concentration of elements of interest. And that background from the X-ray tube, again, reduces precision and sensitivity. So that's the traditional XRF. Moving on to what we're calling advanced XRF, HDXRF, sorry, which is again what XOS has with the Petra series. So in this case, you'll see a different diagram, slightly different, where the polychromatic X-rays are directed first to a doubly curved crystal optic, which is XOS patented technology there. And then from that optic, doubly curved selects peak. It basically filters out the background. Sorry, I have an obstruction here on my slide. Hold on. Sorry, the doubly curved crystal optic selects peak excitation and then filters out that background, causing energies. So, you know, that optic essentially serving as a filter. Next, the optic focuses the beam of monochromatic X-rays to the sample after the optic. And now you'll see the optic has now eliminated the background causing energies. So a much cleaner peak. So, and then that's where the fluorescent X-rays from the sample are collected by a high-resolution silicon detector. And then the background drastically is reduced to the monochromatic excitation. And that is HDXRF. So what do we have? I mean, what are we able to achieve with the Petra with this advanced precision? We have a higher signal to background ratio, an improved precision, and lower LOD. And you can see the difference there in the chart, and the orange is polychromatic with our competitors' traditional XRF, and then and then in the blue, the monochromatic excitation that XOS is here. So a much different signal and noise ratio. On the right, there's those LODs again for all of the elements. Next. So when we talk about advanced workflow, reliability, and robustness, as I said, we do have an autosampler feature, just to give everyone an update. So earlier this year, we put the autosample on hold to do a redesign to address some issues we had actually had in the field. And the redesign was successful. Design was successfully tested, and as we speak, the pilot testing is going on, and which will be completed mid-October to prove out on some builds we did. So we will know then through successful pilot testing when we can just start selling it again, and we expect that to be shortly after, so probably end of October, early October. So if anyone has an analyzer or wants to purchase an autosampler, if you have a single cup and you want to upgrade it, you'll have to wait till then, and it's not too far from now, so it's around the corner. So this here's how it works. It's a continuous analysis with 8 positions. That QR technology is available to enhance the workflow, which of course eliminates transcription errors, reduced idle time in the lab, and removes the need to track samples. Truly automated workflow is how it works. So you can use an integrated scanner we have in the software, or you can use the on-screen keyboard to enter sample name, scan the sample QR code, and insert into Autosampler. And then you select the preset measurement configuration. The QR code is scanned in the measurement chamber to retrieve sample name and measurement configuration. And then the measurement begins automatically. And when it's over, the sample is ejected and the next sample in the queue is measured. So again, as I started to say, the autosampler is an optional add-on. It can be added to an existing unit that's out in the field now, or it can be purchased on a new one, of course. And the QR coded cups are not mandatory. You can use standard XRF cups if you wish. So this is something we're very proud about. It's unique for the 4294 analyzers. Both the Petra and the Petra Autosampler were designed with the fast-paced environment of modern petroleum labs. And here you see a vertical sample introduction, which ensures spills or leaks are directed to an easy-to-clean drip tray away from the detector. So you first put the sample in the chamber in a horizontal position, and then as you close, it switches over to a vertical position. All components are field serviceable for rapid service turnarounds. As far as printers are concerned, you can use external inkjet or network printing, and that ensures that a broken printer will not prevent continued analysis. There are models out in the market you might be familiar with that when the printer fails, an integrated printer, the analyzer will shut down, it won't work. So they don't have that problem with the Petra series. Workflow reliability and robustness, a little more into that. So in addition, that sample chamber in the vertical is very helpful for things like settling in crudes. So you can see in the actually in the diagram on the right, which is diagram 1, traditional horizontal placement of the sample, settling of particulates is in the way to some degree of the X-ray detector. On the left with the vertical, the particulates settle down and the detector is picking up a clear signal through the sample. You don't have that interference. Some data down below in 3 graphs. Basically, it's 3 samples with varying degree of particulate concentration. On the left, it's a high particulate sample. You can see with traditional XRF, we're talking about a sample, it's coming out at 0.54% sulfur. With the Petramax in that vertical chamber, without the interference, it's picking up 0.93% sulfur. That's quite a difference. That's a problem. In the second example, there's sort of we call a common level typical particulate concentration. You see a difference, traditional testing at 0.73, and then the The Petra Max giving you 0.85. Again, that's significant. And even in samples on the third example, you'll see very little particulate. There is some difference, I think 1.28 versus 1.31 sulfur. So that vertical chamber is a big win for us. We think it's a great feature for the labs to help them produce more accurate data. So when we talk software, it's our next generation software in the Petra series. Allows for preset measurement configurations. Again, that QR integration to avoid transcription and errors. And other features include custom calibrations, on-screen averaging, custom reporting, and some more things. So it's a very simple modern touchscreen interface. Stores up to 30 calibration curves, linear or quadratic settings. You can do data transfer over Ethernet or USB. It does have LIMS integration in the software. It can hold thousands of measurement files, and you can print calibration curves and statistics. So to sort of sum it up, the advantages of Petra technology is direct measurement of the sample, no combustion or wet chemistry needed, very simple design with that vertical sample chamber for increased reliability. Measurement of low sulfur and metals on the Petra Max, such as nickel, vanadium, and iron. And that advanced software with the QR capability, enhancing workflow and mitigating errors. And the Autosampler, 8-position Autosampler, which we are working on now, as you know, to re-release. So that's the presentation. Thank you to everyone for joining.